Hello there, welcome to the first class of our Plasma Physics 1 course. Today we'll be talking about what is a plasma. Let's give you some brief characteristics of a plasma and why it is important for space physics and astrophysics. Well, usually you will see people saying things like plasma is not as common on Earth, but it is very prevalent in astrophysics. So people will see things like 99% of the universe's matter is in the form of a plasma. This is something that is in Chen's book, famous Chen's book on plasma physics. In his second edition in 2006, they say this: 99% of the matter of the universe is in the form of plasma. Well, if you read the third edition of Chen's book, 2016, they have rephrased that to say that 69% of the universe is dark energy, 27% is dark matter, and 1% is, let's say, normal matter. What is normal matter is baryonic matter. So instead of plasma being 99% of the universe, they have reduced it to a part of the 1% of this normal matter, because we don't know what dark energy is and we don't know what dark matter is. But it seems to be the case that they are most of the universe, dark matter and dark energy. So if you consider only the baryonic matter, we have 1%. And within this 1%, 99% is plasma. That's true, that seems to be true. So that leaves us with plasma being 0.99% of the universe. So we have decreased the importance of plasma from 99% of the universe to 0.99%. But anyway, it's still 99% of the matter that we know. So it's of course it's very important, and it's what we can measure, what we can see, and what we can measure in the universe is that which is not dark. So plasma is very important, and if you're going to be studying ionosphere or solar wind or the sun, you need to know plasmas. So what is a plasma? A plasma, well, do not confuse plasmas with, what is this? Let's go. Do not confuse space plasmas or physics plasma with blood plasma, okay? Although the name comes from the blood plasma, they have borrowed the name from there, from that context. In here, we'll treat plasma as an ionized gas. Ionized. Sorry for this. I don't know how to write in this thing. So it's an ionized gas. What is an ionized gas? So it's one in which electrons are separated from their atoms. So you have a few electrons, or at least one electron detached from an atom, will make the nucleus a positive. You have a positive atom, which is called an ion. So an ion is you have an atom with neutrons and protons and some electrons. I'm drawing the old the type of atom here, and then you suppose you have one of them detaching from the orbit of your atom. Then you have an ion here, and you have a free electron as well. So a plasma is a gas in that state. But of course, you may have a small amount of ionization and a large amount of ionization. And in what point do you consider a gas to be a plasma? What level of ionization is required from a gas in order for it to be considered a plasma? That's something that we'll try to establish here formally. So one of the things that you expect from a plasma is that the charges will be interacting from distance due to the Coulomb force, generating a collective behavior. So we may say that plasma is an ionized gas with a collective behavior. So you'll have to handle my horrible letter during these classes, okay? But you have all this in the book. We'll be closely following Bittencourt's book, okay? So we are in chapter 1 of Bittencourt. Okay, so you have to have enough ionized atoms in order to have a collective behavior. It means that you will have electric fields, and those electric fields will will provide the link between ions and electrons from a certain distance, and this will cause particles to move from distance because of this interaction. And if you have enough free charges so that your plasma does indeed exhibit a collective behavior, then you have, you may call your ionized gas a plasma. Of course, there is a formal definition of what is this, this amount of ionization, and we'll try to quantify this through some formulas. Another thing that people usually say is that plasma is the fourth state of matter. What do they mean by that? Fourth state of matter. Well, you have solids, you have liquids, you have gases, and then you have plasma. This, if you have, let's say you have a horizontal line here representing the temperature. This is one of the ways to produce a plasma, is by increasing the temperature. Okay, so if I have a certain element which is in the solid state and we increase the temperature, then the molecules become agitated. You increase the kinetic energy, then they lose their binding and they become liquid. And then you increase further the temperature, this liquid becomes a gas. And then if you keep increasing the temperature, the tendency for this gas is to have ionization of their atoms, and then you have a plasma. So this happens in the interior of stars, in stellar atmospheres, nebula, galaxies, and also most of those things, celestial bodies, are in the form of plasmas. On Earth, you can find plasma. It's more difficult to find plasmas on Earth. It's not as prevalent as in stars. But you do find plasmas here on lightnings and auroras, fluorescent lamps, plasma TV sets. Well, they're not very popular these days, TV sets, plasma TV sets. But anyways, they have been in the past. So the state of matter depends on the kinetic energy of the atoms and molecules. The kinetic energy is also the thermal energy of the atoms and molecules. So the equilibrium between thermal energy of the particles and the attracting forces between particles determines their state. So you may have some molecules or some atoms and they are tied together because of some force. And if you increase the temperature, they will become more agitated, right? And they may be breaking apart. And so this thermal energy is stronger than whatever binding force they have. So they become loose. So you may have the breaking of molecules. And so you have a molecular gas. It may become an atomic gas. And then if you keep increasing the temperature, the atomic gas you may lose some electrons and you produce ions. So then you have a plasma, right? So this is all related to the breaking of the binding between molecules and atoms. Besides temperatures, high temperatures, there are other ways to ionize a gas and produce a plasma. So you have, for instance, photoionization. Where photons are absorbed by an atom, and if they have energy which is larger than the ionization potential of the atom, then you have the energy excess of the photon being transformed into kinetic energy and a pair of electron ion being formed. So this is one of the ways to produce it. And also gas discharge, where you have an electric field applied to a previously ionized gas. So suppose you have a weakly ionized gas for some, in some way you manage to ionize some of your atoms. Then you impose an electric field on it. Artificially you put an electric field in the background. This will accelerate the charges, and these charges may collide with other atoms, and then through collisions they may ionize the other atoms. So you have an increased level of ionization through this electric field. So this is gas discharge. So when you talk about collisions, here, since we have charges being collided, the collisions are not like what we expect in neutral charges. In neutral particles, when you have charges colliding, you have collisions through electromagnetic fields. So the interactions between charges is through electromagnetic fields. So if you think of interactions between particles and their collective effects, let's say due to the long range of electromagnetic forces, each plasma charge can interact simultaneously with a number of other charges, resulting in collective effects. So you may have things like charge-charge interactions, for instance. Charge-charge interactions. And here you have, due to the Coulomb force, for static charges. So the Coulomb force is like this. F is equal to 1 over 4 pi epsilon naught, where epsilon naught is the vacuum permissivity. Then you have the Q, which is the charge, and we have interaction between two charges. One of them is Q and the other one is capital Q. Then you have distance vector, which is given by this. This is the unit vector pointing in the direction between of the two charges. So we have here Q, and then you have a vector like this, which is this is just a unit vector in this direction. So this is the expression for the interaction between these two charges, where r is the modulus of this vector. R without the arrow is the modulus of the vector. This is the norm square of the position vector, distance vector. Well, besides that, a charge in motion is associated with the magnetic field by Ampere-Maxwell law. So I have this from electrodynamics, you know this. It's difficult to draw this nabla with this instrument, sorry. So you have the permeability of vacuum. J is the current plus permittivity, and this one is repeated here, and you have, if you don't understand my equations, just go to the book and you will understand it. Okay. And B here is the magnetic induction. Which is given. We make a difference between magnetic induction and magnetic field through this constant here. You have this relation between B and H, where H is the magnetic field. Sorry, this is a vector. Magnetic field. And this is the permeability of the medium. And we have this constant here from Maxwell's equations, the permeability of vacuum. Okay, in this basic summary of plasma characteristics, we can also talk about weakly ionized plasmas and strongly ionized plasmas. Weakly ionized are plasmas where the charge-neutral interactions dominate over the charge-charge interactions. So charge, neutral, have some charges and some neutrals, but the interactions between charge and neutrals is larger or much larger than the charge-charge interactions. By the way, I have not talked about the charge-neutrals interactions. This type of interaction, you have neutral and neutral, okay, you can understand that it's normal collisions of particles. You have charge-charge interactions, which are described by Maxwell's equations, and you have charge-neutral interactions. But this is more complex to describe. Usually they go into quantum physics to describe this, so it's outside the scope of our course. But anyways, if you have more charge-neutral interactions than charge-charge interactions, then you have a weakly ionized plasma. Whereas if you have more charge-charge interactions, charge-charge interactions dominating, are much larger than charge-neutral, then you have a strongly ionized plasma. And you have also the fully ionized plasmas, where all particles are subject to Coulombian interactions. All right, let's think about some basic plasma phenomena now. Usually plasmas are great electric conductors, so it's difficult to find electrostatic fields due to the mobility of electrons. The presence of density gradients leads to the diffusion of particles in dense regions. So those particles in those regions are diffused to regions with a smaller density, and due to the smaller mass, the electrons diffuse they diffuse faster than the ions, leading to the generation of polarization electric fields due to the charge separation. So the field increases the diffusion of ions, and it decreases the diffusion of electrons, leading to the diffusion of both species to become approximately the same. This diffusion is the so-called ambipolar diffusion. Oh, sorry, need a white color here. I don't know if it's ambipolar or ambipolar diffusion, whatever. Ambipolar diffusion. So basically, you have at a certain time you have a region with higher density of particles. This is in a time t naught. Then let's say that you have the electrons moving much faster than the ions, because they are smaller, they are lighter, so they move faster. So they are diffusing to other regions because the gas is trying to reach an equilibrium, so it will spread away to make it homogeneous. Then this charge separation will create an electric field. All right. Then this is in a time t1. Then, because of this electric field, you'll have the tendency for the ions and the electrons to get closer together. So the electric fields will lead the electrons back to the ions and the ions back to the electrons. And so you have approximately the same diffusion of both species. Okay. Another thing that we have is in the presence of waves. If you have waves and charges, different types of waves may lead to dumping of and instabilities in the plasmas. So let me see. So you may have electrostatic and electromagnetic waves in your plasma. So the interaction of those waves with particles will produce either dumping of the waves and acceleration of particles, or you may have the transfer of energy from particles to the waves causing instabilities. So let's say that you have an electromagnetic wave and you have some charges. So this interaction between the particles and the waves may lead to, as I said, the acceleration of particles. If you have acceleration of particles, then you will have the damping of the waves. So the amplitude will go down. Okay, and the particles will be accelerated. Or you may have a transfer of energy from the particles to the waves. So in that case, you'll have instability. Instability happens when the amplitude of the wave keeps growing. So you have this transfer of energy from the particles to the wave may lead to the instability. So we're going to study this more deeply along the course. Actually, I'm not sure if we see this in Plasma 1 or Plasma 2 and Plasma Physics 2. But Landau damping and lots of wave instabilities are studied. I think it's Plasma 2, not Plasma 1. But anyways, I'm just giving you a basic explanation, basic review of a few phenomena that may take place on plasmas. You may also have radiation emission. If you have a magnetic field, let's see, you have a background magnetic field, you have the tendency of particles to have a circular motion around this field. We'll see this in chapter, I think it's chapter 2. We'll see that the presence of magnetic fields leads to this type of cyclotron motions around this field. So the particles are spiraling surrounding B. So there is an acceleration in this circular motion leading to cyclotron radiation. So because you have acceleration, angular acceleration, centripetal force. So the production of radiation is also present in plasmas. So you have waves, you have instabilities, you have radiation, you have damping, you have all sorts of phenomena taking place. So a very complex configuration of this gas. Once you add a magnetic field, electric fields, then what was already complex gas dynamics becomes even more so. Well, let's think about the criteria for plasmas. So what constitutes mathematically a plasma? So there are a few characteristics that a gas must have in order to be called a plasma. I have already mentioned that it has to be ionized and ionized to such a level that you see collective behavior in it. But in mathematical terms, how do we quantify that? That's what we're gonna try to do now. This is section 2.1 of Bittencourt's book. So it's macroscopic neutrality. Okay, in the absence of external forces in a volume sufficiently large to contain a large number of particles and sufficiently small compared to length scales of the variations of parameters like density and temperature. So you're looking at a region of your space where temperature and density do not change too much. Then the electrical charges are zero. The total electrical charge is zero in a plasma. So you know you have ions, you have electrons, but the average charge is zero. Of course, I'm talking about microscopic scales. If you look closely, if you take the space surrounding an electron, for instance, you will see that the charge in that region is negative. But that's in a microscopic scale. But if you take a slightly larger amount of space, then you will have that charge being compensated by the presence of some ions. So the total electrical charge in that region will be zero. So there is approximately the same number of positive and negative charges per element of volume for the gas to be called a quasi-neutral. So you have actually a quasi-neutral gas. So approximately, and we can actually calculate the length in which this quasi-neutrality is true, linked to the concept of this Debye-Shielding. So the plasmas will try to shield potential electrical potentials applied to them. So suppose you have a plasma. Let me see. I have here a plasma. Then you have some ions, some electrons. Okay. The gas is ionized, so ions and electrons coexist in this plasma. Then you add to this plasma a charged sphere. So you have here your plasma, and you added a sphere with some positive charge in it. then what will happen with the electrons is that they will be attracted to this charge, to this sphere, and they will try to shield out this charge, to neutralize it. So they will form a cloud of electrons surrounding this charge. So you have the other ions there, but the electrons will be attracted to the big charge. These electrons will be distributed in this cloud following a Boltzmann distribution. They will not get stuck to the sphere due to quantum effects, but they will be attracted to the surrounding of this sphere. So there is an electric field here inside this region, in this cloud, because you have the positive charge and the negative charges surrounding. So there is an electric field. But the ions outside this cloud do not feel this electric field because it's just related to this link between the big charge and the negative ones. But the question is, what is the radius of the cloud? Supposing that the cloud is distributed in another sphere, a spherical shape, and this cloud, the spherical cloud has a certain radius. What is the radius of this cloud of electrons? This is an important quantity in plasma. This is the Debye length. Well, let's try to calculate it. It's easier to do it in one dimension, so I'll try to do it supposing we have just one spatial dimension. So we have phi, which will be the electrostatic potential. Of the sphere that I have just inserted. Could be any point charge in the plasma, really, but let's suppose that I have just added a sphere. Then there is the electric field, which is given by minus the gradient of the electrostatic potential. This is just the definition of electrostatic potential. This is equation 1. Then from Gauss' law, we have that the divergence of the electric field equals the density over epsilon, where epsilon is the permittivity of vacuum. This is permittivity of vacuum. And rho is the density. Okay, this is Gauss' law, right? Well, this is equation 2. And if you use 1 and 2, then you have the divergence minus the divergence of the gradient of the Laplacian. Sorry, the gradient of phi, which is the potential. I have this. Then the divergence of the gradient is the Laplacian. So we have the Laplace equation. Let me just put the minus sign to the right hand side. And this is equation 3. Well, rho is the charge density. So what is the charge density? Charge density, we may write it like this. So we have the electron charge times the density, the ion density, the number of ions, and then minus the charge times the electron density, or number density, right? Where for charge we're using this number, approximately times 10 to minus 19 coulomb. Okay, so if we do this in 3, or just put it here, we have the Laplacian of 5 equals minus E over epsilon naught and I minus n E. So if we're doing it in 1D, right? So I have used Gauss's law, where you have the divergence, but the divergence really and the Laplacian only makes sense. This notation only makes sense if you are in 2D or in 3 spatial dimensions, right? Well, since we have Li the mass of ions is much larger than the mass of electrons. So we will consider that the ions do not move considerably during the time of our experiment with the plasma in comparison with the electrons. So we'll consider that the electrons are fast moving and the ions are static. So if n, this is the n infinite, is the density away from the sphere. Well, far away from the sphere, you'll have Ni approximately equal to the density of ions is approximately equal to the density of electrons, which is basically this N infinite here, right? So from another point of view, according to statistical mechanics, the particles in a thermal equilibrium in a force field will distribute in such a way that the density n of particles in the position x is given by n, the density at position x, is equal to an initial density times the exponential of minus u of x over kb t. So this is basically the Boltzmann-Gibbs distribution, right? Boltzmann-Gibbs distribution. Where u of x is the potential energy. So in our case, u of x is given by minus phi of x times the charge. And what else do we need? Oh, kb is Boltzmann's constant. We are using kb equal to 1.38 times 10 to the power of 23 Kelvin. Okay, T is the temperature. So our gas particles will naturally try to be distributed in this way. This is just thermodynamics. Thus, we have for Ne, the density of electrons, we have N, well, the initial density before we had the sphere would be, or far away from the sphere, would be N infinite. That's what we said here, right? So this is n naught. Then this is times epsilon and minus u. So it will be phi of x times e to the power of 5x times e over Boltzmann constant times temperature. Now, if we use this quantity in 4, where is 4? 4 is this. Oh, here's 4. Okay, so I'll put this here. The density of epsilon, I'll put this value here. So in 4, we have d square f dx square equals minus e over epsilon naught n infinity minus n infinity epsilon 5 of x e over kb t. Okay, so here we have, let's just put n infinity in evidence, so we have phi e kb t minus 1. So this is equation 5. Well, now we're going to expand this exponential here in a Taylor series. So what is a Taylor series for an exponential function? The Taylor series Taylor series of e to x is 1 plus x square over 2 plus this way, right? You must be familiar with this quantity. It's basically x to 0. We're expanding and surrounding 0, right? So it's x of 0, 1, and the derivative, and second derivative, and so forth. Okay. So if we use this in 5, we're going to expand this quantity in Taylor series. Expanding phi. Is it phi? No, it's x, this quantity. Okay. And 5. We have d. Let me see it again. So it's okay. We'll repeat this one on the spot and just expand this one. So here is the Taylor series. This 1 over 2 fact then kb t square and higher order terms, and this minus 1 here. Okay, it finishes with a minus 1. We can cancel this with this, and we end up with this series here. So, but we are going to consider that the temperature is much larger than the potential here. So let's just forget about the higher order terms, and we'll suppose that this is a small quantity, so to the square it will be a very, very small quantity, so we can drop it, and this one and the higher order terms. So I'll keep just this first term and the expansion. So supposing kBt much larger than phi e, we can drop higher order terms. And we end up with d phi dx equal to en infinity over epsilon naught, and I'll just keep this term. I know mathematicians hate this, but the physicists do it all the time, dropping terms because they're small. So for all the effects, for us, they are just zero, or as close as zero as possible. Okay, now we can, well, we'll just multiply e by e, so we have e square. This is e square, and it's still here, and the potential, then this here, right? And I'll write it this way. I'll introduce this variable lambda d here, lambda d square, and the phi. This is equation 6. So lambda d is the Debye length. Epsilon kb t epsilon square and f. Okay. This is 7. We'll use it later on. So if you solve, so this is the Debye length. Let's solve this one. Solving 6. I'll do it here. And this is basically why I have used 1D systems, because it's easier to write everything and it's easier to solve the second order differential equation in 1 dimension. It's easier than in 2 or 3 dimensions. So I'll try this. This is a linear second order differential equation with constant coefficients. I'll consider that T, temperature, is a constant here for simplicity. Then the solution is of this type. I'll try something, an exponential solution where gamma is a coefficient, an exponent that needs to be found. So if you insert this type of solution in this equation, so you will derive this twice with x, you get this quantity, right? Then it's equal to 1 over lambda squared d times this. And we end up knowing that gamma is equal to 1 over Debye length. Okay, so we have 2 signs for the possible answer. You have phi equal to, well, we have a constant here, minus x over lambda d. I'll just write in this solution with this gamma. This is a d. And we have also another one. This is the general solution of that equation. I have both possibilities here. This is a constant, and these 2 solutions. But we're dealing with physics here. And in physics, we know that the potential should be decreasing with larger x, because we have a sphere, and electrical potential will decrease as we move away from the center of the sphere, right? So we want decaying electrical potential. electrostatic potential. So this solution is not valid for us. Okay, so we'll drop this because the potential should decay with X, actually with this, right? So this is not interesting. Well, actually, I was considering that X is larger than 0. It could be negative X as well. Then I would drop this one. So if X is positive, I would keep this and drop this. If X is negative, I would keep this and drop this, right? So what actually I'm going to do is to write this like this. Oh, sorry. Let's write it like we have initial potential times the exponential of minus the modulus of X over lambda d. Okay, this is the solution for the potential. So we have here, this is the most important thing here, the definition of the Debye length. We may have some observations here. Equation 7 shows that the cloud becomes thinner if you have smaller temperatures or a larger ion concentration. So this will give you the radius of the cloud of electrons, right? So if you have higher temperature, then you have a larger cloud. Or if you have a higher concentration of ions in your plasma, also, then you have a thinner cloud. Key 7. What is that? The cloud is thinner for smaller temperatures. Or higher density, ion density. Another thing is that if you have a domain L much larger than the Debye length, every time a local concentration of charges or a charge with an external charge is applied to your system, your plasma, then they will be shielded by a cloud of electrons, a spherical cloud with the radius small compared to L, and they will leave most part of your plasma free of large electric fields. So in this case, the plasma is quasi-neutral. It's a quasi-neutral gas. Because it's not really neutral, because you have a charge here, and you have the electrons. So you will have electric fields, sorry, it should be pointing this way, right? You have electric fields here. Inside your Debye sphere, you have all sorts of electric fields being felt by the charges. But outside the electric field, if your length scales are much larger than the Debye length is the radius of the sphere, then in most part of your plasmas, you don't feel, the charges here don't feel any electric fields. They will not be feeling it because of the shielding of this charge. So it's neutral all surrounding the sphere. Okay. So in that case, outside the Debye length, you will still have you may have away from this the number of ions approximately equal to the number of electrons, which is this, right? Here, not around here, because electrons have moved here, but away from the Debye sphere, you will still have a quasi-neutral gas. And this is just the plasma density. Of course, this is just valid away from the Debye sphere. What is the number of electrons inside the Debye sphere? This is easy to compute. Number of electrons inside the sphere or the cloud. Oh, it's just the volume of the sphere times the density, right? So this number is, the volume of the sphere is 4/3 times pi times the radius square. The radius is just the Debye length square, and this is the density, okay? This is called the number, the Debye number, sorry. Debye number. So what we're trying to do here is to quantify what I have qualitatively said in defining the plasma. Plasma is quasi-neutral gas with collective behavior. So it's ionized, but it's quasi-neutral, and you have collective behavior. But how do you measure that in numbers? So we have a few numbers here. You have the Debye length, you have the length scale of your system. So your system must be much larger than the Debye length for this to be real, in order for you to have a quasi-neutral gas. And you must have a large number of particles. The Debye number must be large. We should have, in order to have a collective behavior inside the sphere, collective behavior inside the sphere or the cloud, if the Debye number is much larger than 1. Or in other words, you may have this. Sometimes they write it this way, just this part here. Sometimes they write it so this way, or sometimes they write the condition like this, or like this. And sometimes they use, for the same definition, they use G, which is equal to 1 over electron density times the Debye length square. So it's 1 over this, right? So this is called the plasma parameter. The plasma parameter. In this case, G should be much smaller than 1 for you to have collective behavior. So it means that you need a lot of particles inside the sphere, because you don't want it to behave like a two-body interaction. You have one ion and one electron, so that does not produce collective. That's not what we call collective behavior. So we want to see a lot of electrons moving according to the electric field produced by the positive charge. So if an external source disturbs the plasma and takes it away from the equilibrium and causing the charge separation, the electric field formed will tend to lead the electrons to move in the direction of the ions to restore the neutrality. because of the inertia, the electrons will move away from the equilibrium position, generating an electric field in the opposite sense. This will repeat periodically with the frequency known as the plasma frequency, which can be shown to be like this. We'll show this later, but you see, you have a charge, and then we had electrons. They will move towards this. So, but then they will overshoot and will come this way. Then they will go back to here. So the electrons will move this way and this way and this way, trying to reach the ion. So we have this frequency of the oscillation called the plasma frequency, and it's given by NE square over the electron mass and epsilon naught is to 1/2. This is the plasma frequency. So I have lots of definitions here. I think I'll use different colors for them. So this is plasma frequency. We have also plasma parameter. What else? We have the Debye number. This is related to the plasma parameter, but it's written in a different way. What else? Okay, this is it, right? We have, yeah, this is the Debye length. Let me follow on. Well, since you have this plasma oscillation, the plasma frequency, the electrons will be moving, but there are neutral particles in your plasma as well. So you may have some collisions of the electrons with those neutrals. Well, in a normal gas, you have lots of collisions, but you don't have collective behavior because you don't have the electric fields conducting the motions. But here in the plasma, you have both things. You have the collisions with neutrals, and you have the plasma oscillations. But in order for you to have your gas behaving like a plasma with a collective behavior, we want to have the frequency of collisions much smaller than the plasma frequency. Otherwise, the plasma will behave mostly like a neutral gas. We don't want that. So in the plasma, we want a low frequency of collisions in comparison with the plasma frequency. So we may write that in this way. We want the frequency WPE, which is this one, larger than the frequency of collisions of electrons with neutrons, okay? Or you may write it this way. You may say that nu of PE is larger than nu of UN. So this is the plasma frequency, not really the plasma frequency. This time it's the plasma frequency divided by 2 pi. So this is plasma frequency divided by 2 pi, and this is the frequency of collisions between electrons and neutrons divided by 2 pi. So this is a different way of saying it. We may even write alternatively that WPE times tau is larger, or this is an alternative way of saying the same thing. Times tau is larger than 1, where tau is 1 over nu En. So 1 over the frequency of this normalized frequency of collisions between electrons and neutrons. So the plasma frequency is larger than this frequency. So the ratio is larger than 1. Tau is the time, this average time between in which electrons travel between collisions. So this is tau. Okay, so we have more. Frequency of plasma is larger than the frequency of collisions. In summary, we can define a plasma in this way. Criteria for plasma definition. First, we want the ion density approximately equal to the electron density. I have mentioned that. Second, we want a system which is much larger than the Debye length, so that the plasma may actually behave like a quasi-neutral gas. This is a quasi-neutrality conditions. Third, we want the Debye length square times the electron density much larger than 1. This is for collective behavior. It means we want a large number of particles inside the Debye length behavior. And fourth, we want the plasma frequency times tau larger than 1, where tau is defined as above. So we want the plasma frequency larger than the frequency of collisions, so that the basic behavior of the plasma is controlled by electromagnetic forces and not by hydrodynamic forces. Okay, so this is our definition of a plasma. If your gas satisfies all 4 conditions, then you do have a plasma. As an example, in the ionosphere, we have the density of electrons equal to 10 to 12 meters per meters cubic, and temperature is about 10 to 3 Kelvin. That will give you a Debye length of about 10 to minus 3. This is not very readable. 10 to minus 3, okay, meters. All right, or more precisely, if you want to compute it carefully, we have this, right? KB T over E square and E. Let me see if this is correct. Debye length, where is it? Okay, that's it. Debye length, that's correct. Then this will give us, well, this is a big number, 8.85 times, sorry, this is a point, right? 8.85 times 10 to minus 12 for this, times 1.38 times 10 to minus 23 for this, times 10 to 3 for temperature, over The charge is 1.6021 times 10 to minus what? Minus 19, is that it? Square times 10 to 12. I think that's it. And that's approximately 2.18 times 10 to minus 3. 10 to minus 3. Okay, that's the approximate value, but actually it's more like this. Okay. All right. A few other examples of plasmas in nature. If you look at the sun and its atmosphere, sun and its atmosphere. Believe me, it's difficult to write with this pen here. Sorry. Atmosphere. All right. Then we have a temperature in the interior of the sun is 1.2 times 10 to 7 Kelvin. In the photosphere, well, this is in the sun interior. If you go to the photosphere, then you have 6,000 Kelvin. If you go to the chromosphere, then you have about 100,000 Kelvin. So it's going up, it's going higher as you move away from the core. It's a big mystery in the sun. So why is it getting hotter and hotter instead of cooler? But that's the way it is. And the corona. In the corona, you have 10 to 6 Kelvin. So it's getting worse as you move away from the center. The magnetic field is about 10 to minus 4 Tesla. And the surface it's about 0.1 Tesla in sunspots. Just a few curious numbers from the sun for you. So it's much higher in the sunspots as in comparison with the surrounding surface of the sun. Okay. In the solar wind, we have the electron density of about 5.10 to 6 per meter square, and temperature is about 5 times 10 to 4 Kelvin, and the magnetic field is about 5 times 10 to minus 9, very small magnetic field, Tesla. In the magnetosphere, moving closer to the Earth, then we have magnetosphere. We have, well, let's go to the ionosphere. We have a density of 10 to 12 per meter square. So that's a weakly ionized plasma, T 10 to minus 1 electron volts, or 10 to 3 Kelvin. And the Van Allen belts you have, this is more than 10 to 9, about 10 to 9 per meter square, the density. And the temperature is approximately 1 kiloelectron volts. And B is 500 times 10 to minus 9 Tesla. Okay. How can you study a plasma? Well, we have to consider a few equations for mathematically studying a plasma. So we know the basic parameters that define a plasma, but how can we study the evolution of the electromagnetic fields and the density and all that? So we may have a description based on the charge moving according to the Lorentz force. So if you want to study a plasma with a self-consistent formulation of plasma, if you want to simulate it in a computer, or we hardly will be able to solve this analytically, so you'll probably need a computer simulation anyway. So you will follow this equation for the momentum of each charge. It goes with Lorentz force, and it's given by this. So we have here V is the particle velocity, and P is the momentum, mass times the velocity. And E and B, the electromagnetic field, are given by Maxwell's equations. So we have this for the relation of electric fields and magnetic fields. So you actually have to solve all the equations together in order to know the motion of particles, of the charges in a plasma. So if you solve each one of these equations for each charge, then you have your plasma. Here we'll work with the density will be 1, this is the charge density, so it's 1 over the delta V, the volume of your element, and then you have the number of charges. So it's actually the average charge per volume element, and J is 1 over delta V of Qi VI. In small volumes, delta V. Okay, actually this is hardly possible to be done with a realistic number of particles, because you would have to compute this for every charge in your plasma, so billions and billions of charges. So you don't know how to do this with the computers we have nowadays. So perhaps when you have quantum computers, you will be able to solve this particle by particle with all those equations and simulate a plasma in all its glory with a realistic system. But at the moment, we have a few alternatives. With the computers we have now, we need some alternatives, because this is just too expensive, computationally too expensive, too heavy. Alternatives. Well, you have orbital theory. particles. This orbital theory of particles, we study the motion of each charge in the presence of some electric fields and magnetic fields, specified magnetic fields. So we wouldn't have to solve Maxwell's equations. So study particle motions, particle motion in specified EB fields. This is not really realistic because you would have to be solving these equations at each time step to know the new electromagnetic fields. But as you know, this is too heavy. So we just specified constant electromagnetic fields and see how the particles behave in those fields. So no, this is actually a toy model. It's good to understand some properties of plasmas. We'll do a little bit of that in the following chapters, but it's not a self-consistent description of a plasma. And the other option is the statistical description. Or kinetic theory. Kinetic theory, then we have the solution of kinetic equations for the evolution of probability distribution function in the space. So have equation for the evolution of distribution function, of particles. In space. Okay, so this is another alternative. The third alternative is the two fluids. So you'll treat the plasma as two conducting fluids. When collisions are very frequent, then each particle species can be treated as a fluid described by density, velocity, and temperature. So each plasma, each plasma species can be treated as a conducting fluid. With density, velocity, and temperature. This is just valid if you have high density plasma. So it's not a good option if you're trying to model, for instance, the solar corona or the solar wind. Sometimes it is done with this approximation, but it's not the best way. You really should do some kinetic theory. And then we have the single fluid approximation. A single conducting fluid. This is magnetohydrodynamics. Or MHD, which is actually what I do in my research. I do simulations of MHD, but It has some limitations. It depends on the scale of the problem, what scale you want to study, and if the plasma has, it's a collisional plasma and things like that. Okay, so this is the end of the first chapter. Hope to see you soon for chapter 2.